Okay, our numbers have stabilized. We got 43 right now. That number probably will climb as time goes on. So welcome, folks, to the August 6th meeting of the Ottawa Centre, the RASC. Special welcome to our visitors and members from the other RASC centres who might be with us. So we've got an exciting program on tonight, and we'll get to that page in just a minute. So Chris, if I can get the next screen, please. Some security things around Zoom. Please be aware that we do not post URLs in the question and answer or chat windows. However, some nefarious people may attempt to do that. If you do see any URLs, like web addresses in the chat or the Q&A, please do not click on them. If you have a question, please type it in the Q&A box. That's the only box that we're monitoring. You're welcome to chat among yourselves with the chat box. But if you have a question for the presenter or for folks who are running this meeting, please type it in the Q&A box. Okay, next slide. So here is tonight's program. We're almost through the introduction. I'll be taking you through the Ottawa skies for August. We have a special video greeting from Gordon Webster, who's out camping right now on the Flow 50th anniversary and the update around that. Very pleased to have Marcus Leach back, giving us an update on the CCRA and what they're doing. And our main event tonight is Bob Olson, who's going to be talking about astronomical imaging. I'm looking forward to that, Bob. Then we'll have a break with the Messier Moon Challenge and followed up by observations. Meeting should be a little bit shorter tonight, I'm hoping. Not that we aim for really short meetings, but we don't have as many observations tonight as we normally do. So hang in there, folks, and let's move on then to members in the news. And this is a former member of the RASC, Mike James, who passed away, and the obituary was just recently, we just recently came across this obituary, so may he rest in peace. Okay, the Ottawa skies for August. So first of all, here are the moon phases for August. So the full moon is on August the 22nd, and this full moon is known by the early Native American tribes as the sturgeon moon because the sturgeon fish of the Great Lakes and other major lakes were more easily caught at this time of the year. It's also been known as the green corn moon and the grain moon. This is the third of 4 full moons in this season. It is also known as a blue moon. This rare calendar event only happens once every few years, giving rise to the term once in a blue moon. Okay, so the average blue moons occur in average every 2.7 years. So next slide. So the days are getting shorter. Sorry, they're getting shorter. That's right. So you can see by the end of the month, the sun is setting at 7:42. Right now, it's about 8:35. So it's better for us. We can get out observing much earlier. And good news is it's getting cooler, so less mosquitoes. We have the Persian meteor showers. This year is going to be particularly good in terms of the moon. The moon is in it's a waxing crescent moon. It's going to be setting early in the evening, so the 12th to the 13th. Any time after the moon is set, it's going to be an amazing time to see the Perseids, as long as you don't have too many forest fires. That's been our challenge right recently, is the amount of smoke cover. So hopefully we'll have some smoke-free nights. Again, when it comes to the meteor showers, they peak on the 12th and 13th, but Perseids are there from July 17th to August 24th. So if you can't make it that night, go with the next night. You should be able to see them. Mercury is not visible. It's way too close to the sun right now. Venus is visible in the evening, although it is setting fairly early, so you've got to catch it just around sunset. Mars is also setting fairly early as well. And Jupiter is visible in the evening and through the night, and it's at opposition on August the 19th. Saturn is visible in the evening, and it's at opposition on August the 2nd. So there we go. Uranus is visible in the evening and through the night, as is Neptune. And then we have our cartoon of the month. There we go. The super duper discount Mart. And I'll leave that for your viewing pleasure. Okay, moving on then. So I am still giving virtual interactive introduction to astronomies for scouts or guides or adults. I've got a 45-minute program for the young kids, sort of 5 to 7-year-olds, and a 1-hour program for all other groups. And I'm actually doing 3 of these for the Ottawa Public Library this month. Those of you who are on the distribution list for the Ottawa Centre have all the details on that. But I am open and taking bookings for this if you are interested. And this is the follow-up to the older presentation for those 8 and up. And it goes into a little bit more depth on some interesting astronomy issues. So again, this one is also being presented as part of the Ottawa Public Library thing I'm doing this month. Okay, so Gordon Webster is going to be speaking to us live via video about the FLOW 50th anniversary. I'm not hearing any audio, Chris.
Sorry, I'm going to have to pause and exit and restart.
You forgot to share your computer audio.
My mistake about not sharing a button, so bear with me for just a second.
Not a problem.
Are you seeing the slide?
I'm seeing YouTube. I'm seeing the YouTube interface.
Sorry, bear with me some more.
Stand by, folks. We're just having some technical difficulties. And Jim Thompson's missing his panelist link. So when you get this resolved, one more thing for you to look at.
Good evening, everyone.
That's good.
As most of you know by now, 2021 is the 50th anniversary of the Fred Lossing Observatory. Rick Scholes and I have been working to create an event to celebrate that anniversary. And we've selected the day closest to the first star night 50 years ago. Our event will be held on September 11th. It's a Saturday. When we first started talking about this celebration, my daughter Julia suggested that if it's the 50th anniversary, we should have a 50 object challenge list, observing list. So we thought that was a great idea. And we reached out to Oscar Echeverry and Taras and Bob Olson and asked them to select 25 objects that they thought would be suitable for an observing challenge for this group. We received their submissions, and Rick and I added a few of our own. We ended up with a total of about 77 unique objects, and we managed to pare that down to 50 objects. That email you should have received by now with the list and a log. Some of these objects you may be familiar with. Some of them may be new to you. Some of them you may find quite easy, and I know a few of them you're going to find quite challenging. But we thrive on a good challenge, don't we? In addition to the challenge list, we've created commemorative t-shirts and hoodies. And we've got some really, really good pricing on them. The t-shirts are going to be $12 each, and the hoodies are $35 each. Again, you should have received an email on this, and there will be an order form included there. There will also be an order form included in Astronauts, in the August issue of Astronauts, which should be out in a day or two. We're suggesting that you pre-order. This will give us a really good idea on sizes, what sizes we need to order, how many of which size. And if you pre-order, it ensures you're going to be able to get the size you really want. The t-shirts and the hoodies will be ready in early September, and there will be some available for purchase at the event on September 11th. If you haven't received an order form yet, for whatever reason, feel free to email me at astronauts@ottawa.rasc.ca, and I'll make sure that you get an order form. For the event itself, we've got a full day of activities planned, and everything's going to start about 2 o'clock on the Saturday afternoon. We're going to have a telescope clinic. Mike Mogadam has agreed to put together a telescope clinic. These have been very popular in the past. And so if your telescope or your mount has got you confused, if it's not doing things, you can't get it to do things you know it should, or just any general issues, this is going to be the workshop for you. Maybe you're more into astrophotography, trying to figure out how to get your equipment to work together as a unit. Maybe you don't know what piece you're missing or what equipment you should be getting. Basically, any astrophotography equipment issues, Paul Clenninger has agreed to do a workshop to address all of those issues. Maybe you're more interested in a traditional approach to capturing what you're observing in the sky. I'm going to be running a lunar sketching workshop. I've got actual lunar craters on hand that you can draw from, and we'll look at a few techniques for doing that. We'll also discuss deep sky observing. We're working on a special guest speaker who has a strong connection to the FLO and was actually there at the founding. If everything goes as planned, we'll be announcing the guest speaker's name shortly. Later in the day, we're going to be doing a barbecue so that everybody can be fed. And following the barbecue, we're going to have a star party. If you've ever wondered about our 18-inch Starmaster, this would be a great opportunity to come out and see it. We will be using the telescope. It will be available for people to view through. So if you've got an object that you'd like to see what it looks like in an 18-inch, or maybe some of the objects that you're struggling to find from the challenge list, this would be a great opportunity. Did I mention that everybody who does the challenge list, who submits their findings, will receive a certificate of completion? In addition to that, everyone who submits the log, their name will be put into a draw that we're for an official 50th anniversary hoodie, and the draw for that will take place at the AGM. So you have until the 30th of November to complete this if you want your name in for the hoodie. Other than that, we'll continue to issue certificates for completion of the list. We've got another special treat involved here. Many of you may remember from an earlier issue of Astronauts, we did a member profile on Ghislain Souris and how he comes out to star parties with his guitar and he sits there and he plays. And he's agreed to do this. He has agreed to come out for the September 11th event, bring his guitar, and he will be playing. And if you've never experienced the night with Ghislain playing in the background, it's magical. You really shouldn't miss this. All of this, of course, is not just weather dependent, but also COVID dependent. If COVID numbers continue to go the direction they're going, there should be no issues. We're in the third stage of the lockdown, which means currently we have an upper limit of 100 people for outdoor events. That shouldn't be a problem, although I hope we're really close to 100 people in attendance at this. I'm sure we can accommodate that at the FLO. If you haven't been, I really suggest that you come. And if you haven't been in a while, you really need to see the changes that have taken place and just come out and celebrate this marvelous facility that we have at our disposal. We will be following all COVID protocols. If you're not vaccinated, if you're not fully vaccinated, please don't come. Masks, of course, will be recommended for most things where you're in small groups, tight groups. We'll have further information on this at the September meeting and as we get closer to the event itself. We do have a rain date set for most of these activities, which is October 2nd. Again, as we get closer, we'll make those decisions. If you've got any questions on any of this, you can reach out to Rick Scholes. You can contact me. Please send in your orders for the hoodies and the t-shirts. Thank you. That's all I have to say about this for now. There will be further updates as we move into September. Take care. Talk to you soon.
Okay. Thank you, Gordon, for that. And here's an aerial view of FLO. FLO is the Fred Lawson Observatory, for those of you who don't know what the acronym stands for. It's located in Benny's Corners, just outside of Almont. And you can contact any of the members here to get directions to that site. Okay, so I'm very pleased tonight to have Marcus Leach. He is with the Canadian Centre for Experimental Radio Astronomy. He has presented here before, and he has some exciting updates as to things that are going on here. So Chris, I'm going to have you flip to his first slide with text on it. Unfortunately, Marcus is driving blind tonight. He can't see the slides, but he knows what's on them. So go ahead, Marcus.
Thank you, guys, and nice to be back at a meeting, at least in the virtual sense. Yeah, so I wanted to give an update on what CCRA has been up to in the last several months. So yeah, you can go to the next slide. So we've been at the Gallipo Center in Smiths Falls since the fall of 2016, and we had a reasonably good relationship with the both with our sort of proximate landlords and the property owner themselves. But in December of 2020, we received a notice to vacate from our sublet landlords. They'd been acquired by a much larger Ottawa-based company, and that company didn't want tenants. So due to municipal politics, also Gallipo was unable to offer us a space. Basically, they were under a municipal order that forbade them from entering into any new commercial leases. So, next slide. So, what were we going to do, and where were we going to go? Carleton University had an undeveloped site outside of Ottawa. We had a thought that maybe we could turn that with their cooperation and so on into some kind of science park. But any plans for that were, sort of had a planning horizon of years from now. So that wasn't going to happen anytime soon. And then COVID hit, and there was just no way that anything like that was going to move forward. So we looked at commercial sites in Smiths Falls. None of them were particularly well located. And of course, they were really too expensive for us to consider. So, other options. Yeah, go to the next slide. There is a former UCDSB elementary school that has been sitting idle for many, many years. And in fact, my oldest daughter went there for kindergarten. And they built a new school just across the road, and the old one has been sitting idle and acquired several years ago by a private individual. So it's on a few acres. It's out in the countryside. It's currently empty, about 6,000 square feet. Unfortunately, the new owner was unwilling to consider any kind of lease options, and they wanted, I think, $600,000 for it, which is vastly more than they paid the school board for it. But you know, that's up to them. We had no influence over them at all. So we thought about, next slide. So we thought about, you know, how are we actually going to come back from this this huge issue? Is there a way where we could sort of adjust our requirements and continue to do what it is we, you know, what we do? So we moved the workshop components, which is both mechanical workshop and electronics lab, into my house. In fact, I'm in part of it right now. The electronics part is in a tiny little room in the front of my house. And I have a mechanical shop of sorts now set up in a shed off the back of my house. So that took care of about 250 square feet of space that we had at the Gallipo Center. But of course, we still need an actual site to put antennas and equipment and so on. You know, is there a suitable field site somewhere? Quite some time ago, Rob Dick had mentioned that he had a place in Rideau Ferry that he'd purchased for his own optical observatory many years ago. It's I think it's about 38 acres, mostly unused. It's flat, mostly treeless, with a lot of exposed limestone that you can attach, you know, radio telescope mounts to. So what we did was we actually negotiated a lease arrangement or an access arrangement with Rob, and we started moving our operations there in March. Next slide. So that's kind of what the site looked like in May when we just started to put some of our bits of equipment and dishes and so on the site. That particular one is the beginnings of the mount for the spectrometer. And then you'll see next slide. And this is kind of what the site looks like as of a few days ago. So we have the spectrometer dish mostly set up. It's not operational yet because none of our receivers or any of that stuff are on site yet. But in terms of sort of electromechanicals, it's pretty much ready to go. In the foreground, you can see one of our 3-meter FRB, that's fast radio burst dishes. There will be 3 of them there this year and maybe more next year. So we got that one put up about a week ago, I guess. And there's 2 more mounts that are pretty much ready. We just need to put the dishes on them, and then it's a matter of wiring stuff up to receivers that aren't yet on site and all of that kind of stuff. Next slide. So what are we going to do given the fact that we got pretty severely interrupted? And there's a saying that, you know, one move is the equivalent to like 2 fires in terms of disruption to your to your operations. So the 21 centimeter spectrometer, which is one of the things that we offer to our educational clients, if you will, was the top priority for moving out there. So we have an all new mount. We did an upgrade from a 2.5 meter dish, or from a 1.6 meter dish to a 2.5 meter dish, which will improve both sensitivity and spatial resolution. We're using the same receivers, same feed, LNAs, all of that stuff. It was just the dish and the mount that is completely new. We have the FRB array that I had spoken about in the previous slide. Initial array of 3 3-meter dishes, fixed pointings, and the plan is to capture very bright, fast radio bursts, like the STARE-2 project did last year. They were able to detect a bright burst from a magnetar at the edge of the galaxy. So our aperture sensitivity is much, much, much better than STARE-2, although our bandwidth is narrower, but that's just an issue of how much computation we have handy to us to do those wider bandwidth things. So it will probably end up moving to wider bandwidth eventually. We're also going to split the signals from the spectrometer and add it into the FRB processing array, so that we effectively have 4 different antennas looking at the sky in different directions, looking for FRBs. Next slide. So in terms of, how is this going to evolve over the next few years, the plan is that next year, at some point, we'll expand the FRB array out to 6 dishes. We have dishes on hand for that. And we also have this 5.5 meter dish that we acquired last summer. And we've had various plans for it over the last year or so. The current thinking, next slide, is to actually put it up hopefully next year and make it a relatively general purpose instrument. It's a significant engineering project. The dish surface itself weighs about 1,000 pounds, and it's really quite a bit of engineering to make it work. So the plan is we already have a feed assembly made for it at 21 centimeters and 327 megahertz. When it isn't doing anything else, we're going to have it look for the deuterium signature from the interstellar medium around the North Celestial Pole. The plan is to make it accessible, probably remotely, to other people who want to do experiments that can be done usefully at those frequencies. Probably RASC members. We haven't really decided exactly what the shape of that will be, but a dish like that, 5 meters, it's a useful facility for other people to be able to use. Some of the mechanical bits we already have, and my slide is cut off. Hang on. We need to build a lot of backing structure. We need to build either a transit or an as-L mount. We haven't decided yet. Part of it is budgetary. Part of it is just, do we have the capabilities to do something like that for such a large, heavy dish? And the ground mount will need to be fairly massive compared to the ground mounts for our other dishes. The other dishes don't weigh very much. The wind loading on them is not that large, so they're relatively modest. The 5.5 meter dish will require a more substantial anchoring to the ground, and in that particular location, that means drilling lots of anchor bolts into the rock and pouring lots of concrete. And so that's it for my presentation. And I'm open for questions. I don't know how the question thing works here, so.
If I get any questions, I will speak them out to you. So if folks
Okay,
have any
sure.
questions, just type them in the Q&A. And Marcus does not have a video right now, so.
I don't have video. I don't know why.
Yeah.
I was on a Zoom call in Europe a few weeks ago, and it worked just fine. So I don't know.
It's probably the new Zoom update.
Yeah.
Here we go. Oh, where is the location? Somebody came in a little bit late. Where is the location, your new setup?
Oh, it's part of Rob Dick's property in Rideau Ferry.
Okay, thank you. Any other questions? Okay, well, thank you very much, Marcus. We look forward to further updates, and maybe we'll slot you in a few months, and you can show us some pictures of the 5-meter dish all assembled and working, right?
Yeah, sure.
Sure. Okay.
We'll get right on that.
Get right on that. Okay. Thanks again, Marcus, for the update.
You're most welcome.
Okay, I'm going to turn it over to Bob Olson here. Let me just spotlight you, Bob. There you go. And he's going to be talking about astronomical imaging. So go ahead, Bob.
Yeah, how do you do? The first thing a speaker should consider is who their presentation is aimed at. Imagers already know it all. Beginners get swamped with the amount of new information. Visual observers don't care. So everybody else pay attention. I think this leaves science geeks and the idly curious. My goal is to make you want to try imaging. And why would I want to do that? Maybe misery enjoys company. But the most satisfying thing is to annoy all my visual observers who describe astro imaging as the dark side. Next slide, Chris. Why would you put a camera on a telescope? Next image. Well, you can see deeper. You'll see things that you'll never see naked eye. Red is invisible, as an example, in dim light. And this is very difficult. This horsehead is very difficult to see visually. Next image. Hickson 50 is a magnitude 18, which I wish you good luck trying to see with a telescope. And it's about 2 billion light years away. Next. Leo 1 is 11th magnitude, which you can certainly see if it wasn't sitting beside some Regulus, which is 9,000 times brighter. Shows up pretty easily in an image, though. Next. Souvenirs, a good reason to have a camera. We all have souvenirs from photographs that we've taken over the years. In 2017, next. I witnessed the partial solar eclipse in Saskatoon. You can see a couple of sunspots. This was taken with a cell phone through a pair of binoculars. Oh, and there was a filter on the binoculars. Next. Everybody likes comets. Next. In 2019, there's a transit of Mercury. And it sure didn't show up very well, even in this image. But it was interesting, souvenir type thing. Next. 2 weeks ago, the forest fires clouded out my sky, and the moon was cherry red. Fascinating. All the blue light from the moon were being bounced off by the smoke, and we're left with red. Next. You can do science with a telescope and a camera. There are always people looking for where supernovas are. And if you happen to be the first one to spot one, you become famous. Next. Comets, same thing. Get a comet named after you if you're the first one to find one. Next. Pretty pictures. And this is what I really enjoy. Next. The Orion Nebula looks fabulous visually, but it looks better in an image. Next. And next. According to Ginny, I scored big time on this one. Next. why are we able to do astro imaging now? This is kind of new. You know, it hasn't been around for 2 generations, for example. Telescopes haven't changed much. They might be a little cheaper now than they used to be, maybe a little bit better, but not a ton better. Mounts are better and more available now than they used to be, but not spectacularly so. They can be computer controlled, which is nice. Okay, next. It was the invention of the CCD sensor, 1969, and in 2009, they won the Nobel Prize for Physics for this invention. Next. The first camera was invented 6 years later by Kodak. I just absolutely love the tape deck image storage, and it sure looks convenient to carry around. Next. The first camera that was commercially available that I know of was 6 years again later, and it looks just like a modern camera to me. And again, I love the floppy disk image storage. Next. And 7 years later, this camera saw the first light, and it was used by Michael Barber, Alan Holmes, and I'm hearing somebody else. Matt Longmire for guiding their telescope while studying gamma ray bursts, and they were amateurs at this time. Okay, next slide. Next year, they decided to sell the idea of using CCD cameras to do guiding, and this was one of their guiders. And Santa Barbara Instruments Group is now owned by Doug George, who is an Ottawa RASC member. Next. The cookbook camera was published in 1994 by Richard Berry, and it gave instructions on how to make your own CCD camera. The book was available with a kit of parts. Next image. One of our club members, Mike Ziegler, started to build this kit and then decided it was much smarter to buy a camera. I finished the project, and thus the cookbook camera became my first astronomy camera. It wasn't the most convenient camera in the world to use, but I learned lots trying. As you can see, it took you half a day to get this thing connected to your telescope. Next. Why not use film? Instead, why did we not use that? It was invented by George Eastman in 1888. So it's been around for a while. Next slide. It's just not satisfactory. Long exposure images need to be guided unless your mount is better than anything we can afford. If you don't have a CCD camera connected to your computer to guide your telescope for you, you need to do visually. Staring through an eyepiece for hours on end, trying to keep a star on the crosshairs is emotionally and physically nearly impossible. The other major flaw with film is a characteristic we call reciprocity failure. Due to the way light registers in silver salts on the film, dim light is a problem. The salt crystals need to be hit twice in a relatively short time by a photon to register. And in dim light, the second photon may not arrive in time and will therefore not be counted. And the last thing that's just a nightmare with film is, how do you focus your telescope? Take a picture, send the film to the processor, wait a week, adjust the focus and repeat until good focus is established. That's impossible. And then the temperature changes in your telescope. You have to start over. There were tricks, but they were all terrible. Next slide, please. Most amateur cameras use CCDs, but CMOS cameras are now starting to take over the market. I think all DSLRs now use CMOS sensors. I will use CCDs as my examples, but CMOS chips work in nearly the same way. The sensor is divided into chunks called pixels. These are really small, 3 to 6 microns across. A sensor less than 2 centimeters across will have millions of pixels. Next slide. This is a cross section of a pixel. Photon of light hits the sensor and an electron is knocked free. At the end of the exposure, the number of electrons in each pixel is counted. Many electrons means a better, brighter picture. The electrons are trapped in a part of the sensor called a well. The percentage of photons that actually produce electrons is the quantum efficiency of the sensor. This ranges from 50 to 95%. Higher is better. So, 50 to 90% of those photons will knock an electron free. What are the problems that we need to overcome with this CCD idea, though? Next slide. The electron well can only hold so many electrons. What happens if more electrons are knocked free than can be stored in the well? In very early CCDs, they would overflow the well and create havoc in nearby pixels. This was called blooming. In modern CCDs, these overflow electrons are bled away by conductors, but even so, the pixel will be registered as white. Full is full. There's no such thing as white or white. This means the picture is overexposed, or at least that this part of the picture is. We call it clipping. The way you handle this is with a shorter exposure, or get a camera with a deeper well. Deeper wells are better. Next. CCDs introduce noise into the images. They're complicated electronic devices. There's all kinds of calculations and electronic operations occurring, and these operations are not perfect and create noise, which results in a noisy image. Some of these are read noise. When the electrons are counted, our count might be high or low. This happens once every time a picture is taken. Electrical noise, which is just the electrons produce noise, the electronics produce noise. Next slide. It turns out that some electrons are spontaneously generated in the sensor with no light hitting the camera at all. This random current is called dark current and is dependent on the temperature of the sensor. Thus, if you cool the sensor, you can reduce this current. Every 6 degrees cuts the dark current in half. Go down 30 degrees and the random current or noise is 32 times less. All modern astronomical cameras are cooled and usually to at least 30 degrees less than ambient. Dark current is also directly related to the length of the exposure. This means twice the exposure, twice the noise. This really sucks as we want long exposures to get a decent image. Modern sensors have much less dark current than the old clunkers like the ones I use. Next slide. Before we go any further, I think I should mention the biggest problem with astronomical imaging. It's dark at night when we take astronomical images. This means the pictures are really dim, and I mean really dim. Some of the problems that we have in taking pictures of the night sky are caused when we try to overcome this. Next. How can we make a dim image brighter? Let's look at an ordinary daylight photo that some of you may have seen before. It's a photograph of my imaging telescope after a tree fell on it. Besides the picture, I have put a graph that was generated by Photoshop called a histogram. This graph shows all the shades of gray along the bottom of the graph. Next slide. These go from black on the left to white on the right. The graph above this represents the amount of the picture that has these shades of brightness. As you can see, this picture has a fairly equal distribution of light and darks. The picture has a light sky and a white mount in the picture, so there's a bit more bright tones than dark. This is your typical daylight photograph. Most of the picture is somewhere between black and white. By the way, when I showed this picture, several people asked me if I had submitted a claim to my insurance company. And you know, I never even thought of it. And so I sent them the price of my copy of Photoshop. I'm still waiting to see if I get any money. Next slide. This is an image that's been taken straight from my astronomy camera. That's not exactly true. This is a stack of 20 individual 10-minute exposures for a total time of slightly more than 3 hours. Even with 3 hours of exposure, you can see the picture is very dark, and the histogram is a vertical line on the black edge of the graph. This is a 16-bit image, meaning there are 65,000 shades of gray available for us to use. Since we only can see 256 shades of gray, you might wonder why we want 65,000. That's because all the information is jammed into that single line on the histogram. We are going to take that skinny line and stretch it across the entire graph. Next slide. What I've done is I've stretched it across halfway. Okay. We could actually stretch it the whole way in one step, but it's easier to control if we do it in several steps. Next slide. In this last step, we have stretched it a bit further to about 3/4 of the way across the histogram. If we go much further, we start to lose star colors. When I have been describing this to you, it sounds like I'm stretching the graph like an elastic band. That is equally in all places. But in fact, the stretch is quite complicated and is a nonlinear hyperbolic stretch. The darker areas are stretched more than the bright ones. These stretches are handled automatically by the imaging software. Next. This image is exactly the same as the first one I showed a minute ago, except that it is an 8-bit image with 256 shades of gray. What happens if we stretch this one? Next image. As you can see, the image looks similar, but washed out. If you look at the histogram, it is a bunch of vertical lines instead of a solid curve. The original image had only 256 shades of gray, and we stretched it to 25 times wider. That only leaves us about 10 shades of gray, which, surprise, surprise, looks washed out. If you're going to stretch images, you need to start with a 16-bit image, and it's 65,000 shades of gray, so there's something to stretch. When this happens, we call it combing, because the histogram looks like the teeth of a comb. A serious shortcoming of stretching is that the noise is also stretched. You can think of stretching as increasing the brightness in select areas. But when you turn up the gain on an image, you also turn up the gain on the noise. One of the advantages of taking digital images is that you know what your noise is, and you can subtract it from the image. We call this calibrating an image. We use 3 reference images to figure out the noise. Next slide. We take a photograph with the shutter closed on the shortest exposure the camera can handle. The only thing that should be registered in this picture is the noise in the camera itself. As you can see, the picture is black, but then again, my picture of the rosette started out as black. Next slide. This is the biased frame, the same image that you just saw that has been stretched. If we did not subtract this bias from our picture before we stretched it, this noise would be superimposed on our picture. Next. A dark calibration image is used to remove the spontaneously generated electrons that we call dark current. This picture should be the same length as the exposure that you took, in my case, 10 minutes. The shutter is closed, so this picture should be black. Okay, next picture. If we stretch it, this is what we get. Modern cooled cameras are pretty quiet and don't have a ton of dark current, but there is some, as can be seen in this stretched dark frame. There is a general uneven speckling over the photo, and I have a warm column that generates more dark current than the rest of the sensor. Again, we subtract this from the image. Next frame. Telescope optics are not perfect, and they are way less perfect than well-designed modern camera lenses. They do not illuminate the camera sensors evenly, and since all this stuff stays outside for extended periods of time, dust is a serious problem. The solution to this is to take a picture of a smooth, bright gray object. We use a light box or a luminescent panel. Even a white or bright gray wall will do. Here is an example. It looks gray, and except for a little darkening in the corners, it looks pretty flat. Thus the name. But will it stand the stretch test? Next image. Clearly not. The corners get much darker, vignetting, and there are some dust donuts in the optical train. What we do is we tell the computer that this image is flat gray, and then it adjusts each pixel in our astronomy image accordingly. If a pixel in the flat is dim, then the gain is increased at that pixel in our astronomy image. And if the pixel is in the flat is bright, the gain is reduced, thus balancing the final image. Astronomy imaging software has a ton of smarts, so calibration is mostly done automatically. In conclusion, if you're going to stretch a dim astronomical image to make it brighter, then using biases, darks, and flats is a good idea. You will end up with a less noisy image. If you are going to take a picture of Aunt Matilda in a brightly lit room, then you will not need to stretch the image, and calibration will not make much difference. By the way, increasing the brightness, the ISO, or the gain of a snapshot of Aunt Matilda in a dim room will result in a noisy image, as you are increasing the noise as well as the brightness of the final photo. Next picture. The randomness of light arriving at a camera is called shot noise. Light arrives at the sensor after being focused by the telescope in discrete quantums called photons. It does not wash evenly over the photo, but arrives at specific points. In this photo, taken from Japanese Wikipedia, we have 9 photos, each exposed to different lengths. The first exposure is so short that on average, only 1 pixel in 1,000 is hit by a photon. In the last photo, each pixel on average is hit by 100,000 photons. The random nature of light's arrival is easily seen in the dimmer photos. The one photon per pixel photo looks like someone sprinkled pepper on it. One easy way to reduce shot noise is to take longer exposure images. This can be done using one long image or a series of short images that are added together. The advantage of one long image is the reduction in read noise and the reduced number of image files. The advantage of short exposures is that if something goes wrong, you only lose a short exposure. As an example, when your neighbor turns on his lights, you might have to trash 1 minute exposure instead of a 30-minute exposure. This is much less painful. It is also much easier to guide for a minute than for 30 minutes. Modern cameras have a much lower read noise than old ones, thus the advantage of long exposures is less true nowadays. Just to be clear, long exposures have more noise than short ones, but the signal increases faster than the noise, so the signal to noise ratio is better in long exposures. The question I often get asked is, can I just stack 10 of the same image instead of 10 separate images? They are all of the same object? And the answer is absolutely not. The noise in separate images is in different places in each image, thus tends to cancel or even out the differences. The noise in a single image is in the same spot in every image. So if you just amplify it by 10, the noise will go up by 10. And the signal will go up by 10 times too. There is no improvement in the signal to noise ratio. You have to use different photographs. Next image, next slide. This is an example of a single 10-minute exposure of the Whirlpool galaxy. Next image, please. This is the same image stretched. Notice the noisy background. Next image. This is a stack of 46 10-minute exposures for a total of almost 8 hours. Next image. This is the stack of images when stretched. Next image. This is the single image and the stack of images, 10 minutes, 8 hours. Not much difference. And if you look at the histograms, they look identical. Next image. Single image, 10 minutes long, 8 hours image, and they're stretched. You'll notice that the stack is a better image than the other. It's less noisy and more detail shows up. Our decision as imagers boils down to this. Is the improvement worth the extra time? 10 minutes, 8 hours. It's your call. Next. Everything I've said so far has referenced a monochrome or black and white sensor. There is no color information whatsoever, but my images are all color images. How is that so? Next slide. It turns out the human eye has 3 different types of color sensors. These would be red, green, and blue. Every other color is just a combination of these 3. If I correctly combine red, green, and blue in an image, I can produce a full color image. Next slide. For me to get a color image, I alternately take pictures through red, green, and blue filters. Next. These filters are mounted in a filter wheel and rotated electronically in front of the camera, so I don't have to do it manually. The resultant images are combined in astronomy imaging software. Next. But every camera that we own that is not an astronomy camera doesn't have filters that are rotated in front of the lens. Next image. DSLRs and cell phones use sensors that have individual filters installed on each pixel. There will be millions of pixels on the center, so these individual filters have to be extremely small. This arrangement is called a Bayer's mask. Next image. As you can see, the red filter lets in red light, the green filter lets in green, blue, blue. And they hit different pixels. You will also notice that there are twice as many green as there are red and blue. Green is in the middle of the spectrum, and it has more to do with how we see than the red and the blue. Okay, now what happens if we use a narrow band filters? In astronomy, we often take pictures using hydrogen alpha, which is a red, deep red, and we use oxygen 3, which is a cyan. It's halfway between green and blue. And so in those cases, they only light up some of the pixels on your camera. The rest of it's blocked. So in that case, a monochrome sensor is better, one without these Bayer filters. But for just general use, they're both useful. Okay, next slide. Another question I get all the time is, what's my equipment and what would I recommend? The only advice I might pass on is the types of telescope doesn't really matter. Good images can be produced on any type of telescope. Next. That is refractors, reflectors, Newtonians, and Schmidt-Cassegrains. What does matter is the quality of the optics. Next. Brands and costs are obviously factors, but not the only factor. The best advice is to ask for advice when you are thinking about making a choice. In general, it is easier to get a good picture using a short focal length telescope rather than a long focal length. As a rule, short focal lengths are easy, long focal lengths are hard. Next. What telescope mount should you use? If you're going to take long duration exposures, your mount must be equatorial. That is, it rotates with the Earth in the opposite direction. The long-time favorite has been the German equatorial mount, as shown here. And there are some modern derivations which are probably work very well. This piece of equipment is probably more important than the telescope. So I would suggest spending your money on the mount rather than the telescope. It must track well and be steady. Go-to will increase your imaging time by decreasing your search time. Computer control is very convenient. Next. If you're going to take short duration planetary or lunar images, any mount will do. In our club, the best planetary images and lunar images are being produced on our club's own superb 18-inch Dob at FLO. In summary, the mount must be steady and track well. A go-to mount will increase your imaging time and decrease your search time. If the mount can be controlled by your computer using a planetarium program, that is also very convenient. Next. Where should you image? Dark skies are very helpful, but images can be taken in the city or even when visual is impossible. Dark skies produce images with less noise, but city images are way better than no images. As you can see, I'm in a kind of a greeny blue area. Not too bad. Next. Sharpening an image is just what it sounds like. The details in an image are made clearer. Smoothing is the reduction of noise in an image. There's a great deal of software available to do both of these. Astronomical images are often noisy, and we would like to see detail better. This makes sharpening and smoothing very attractive, but be careful that you don't make your images look artificial. And remember, it's a hobby. There is no level of quality that you need to achieve. Just have fun. Next. If you have any questions about imaging whatsoever, feel free to give me a call or drop me a line on email. I love talking about imaging, so don't be afraid to ask. But there are many other imagers in this club, all of them very talented, and all of them like passing on their knowledge. Ask any of us. Have a great day.
Thank you very much, Bob. Maybe you could just sort of say what your email is for those who don't have it.
It's r.olson@bell.net. That's just r.olson@bell.net.
Okay, perfect. Yeah, just in case people want to get in touch with you. Are there any questions, folks? Let me see here. Question here. How is the Malincam video image camera different than other CCD cameras?
Well, the truth is I don't know very much about it. There's lots of guys in this list that do. I think it's fairly similar, except it takes movies instead of still photographs. I don't actually know much about it, though.
I think Jim is on the call here as a panelist. Maybe you could speak to it, Jim.
Sure. Is my mic working okay?
Yep.
Yep. So the original Malincam that was based on a CCD sensor developed in the mid-90s. It's an analog video camera, and it's intended for observing, not for imaging. But more recently, like in the last 5 years or so, Malincam has also started selling cameras that would be considered more traditionally used for imaging. So they do have products for sort of both applications.
Okay, thank you. Any other questions for Bob? No, I think that is it. So thank you very much, Bob. Again, folks have your email if they have any further questions. And it's fascinating this stuff. I learned a lot tonight about how things work. And I've got to get I bought a camera. I know I can connect it to my telescope. I've taken 2 pictures through it in 5 years, so maybe I should up the quantity a bit.
Whatever.
Yes, I know. Okay, folks, so just a second here. I'm just going to remove some spotlights here. Remove spotlight. There we go. So we're moving on to the break, I believe. So Chris, if we can move on to that. There we go. So we're going to take a 5-minute break. Followed by that, we're going to have our observations and observation challenges for the evening. So hang in there. Next slide, please. Here are our 2 images. See if you can guess what they are. Which Messier image is this? And which craters are these on the moon? So we'll have the answer after 5 minutes. We'll see you then. Okay, folks, we're just coming back from the break here. So, Chris, if you can move on to the next slide. There we go. There's the answer to our M&M challenge. So hopefully some of you were able to guess what those were. So we got M105 and Hercules and Atlas on the moon. Okay, so we're moving into our observation section here. So next slide. So we have Jim Thompson here. So just give me a second here, Jim, while I highlight you so everybody sees you rather than me. There we go. You're good to go. Next slide, please.
All right, thanks, Dave. So I was away for the past 2 meetings. So this is my first opportunity to present images from the June 10th solar eclipse. On the day in question, my daughter and I hiked to a well-positioned wheat field just off of Innes Road near Blair Road. This first image here shows me with my setup. In the foreground is a mirrorless camera with its stock lens and a white light solar filter. And then in the background is a 67mm refractor with a narrowband H alpha filter. It may look from the photo like I'm wrapped in a cape because I was cold, but in reality, there were a crazy number of mosquitoes and I forgot to bring bug spray. But despite the mosquitoes, the observing site turned out to be really great, and I captured many images. But to keep it short, I've only submitted 2 of my eclipse images to share tonight. Next image, please. So this first image is a composite of shots taken with the refractor, showing the appearance of the eclipse over the course of the period for which I was able to observe it between clouds. Each image is about 5 minutes apart. Next image. The second image is a more detailed shot with the same refractor, captured around the time of maximum eclipse. As you can see, there were a fair number of prominences visible during the event, which added nicely to the appearance of the sun. Next image, please. Other than the eclipse, I have not had a lot of opportunities to observe this summer. This image here shows some nice solar activity that I was able to capture on July 4th while I was at my cottage. Out of the 3 weeks I was on vacation in July, I only had 1 single clear evening of observing. And the next couple images were from that evening. If we go to the next image. So on the particular evening in question, July 10th, I was able to observe one of my personal challenge objects, NGC 6334, the Cat's Paw Nebula. It is a challenge object for me because it is very low in the sky for our northern latitudes. From my cottage observing location on the shores of the Ottawa River, I am able to see low enough to catch this object. This image is a stack of 30 20-second long exposures using a Mallancam Skyraider DS432 camera on an 80mm William Optics refractor. Next image, please. In addition to observing on the 10th using the 80mm refractor, I was also using a 40mm refractor and an ASI 294 color camera. This image is a mosaic of 3 frames from that setup, each a stack of 30 20-second frames. The image stretches from M24, the Sagittarius star cloud on the right, all the way across to M16, the Eagle Nebula, on the left. I had a lot of fun on this evening with this tiny little scope, exploring along the summer Milky Way. I will tell you more about tiny refractors in a future presentation. Thank you.
Okay, thank you, Jim. And Oscar is up next. I just have to find him here. Hang on a second. So you slipped off my screen there, Oscar.
Yeah,
there
no
we go.
worries.
There.
So I just got 1 image to present tonight. This is Messier 95. It's a barred spiral galaxy in Leo. This was taken with a Sustron Edge HD at 2800 millimeters, so quite a bit larger than the, quite a bit longer focal length than the 40 millimeter scope that Jim was just talking about. Presents quite a few challenges with tracking and stuff. So this is a combination of about 3 hours of 10-minute sub-exposures, taken with a Canon 60DA. It's been sitting in my processing backlog for about 2 years. I thought it was about time to finish processing it and present it. That's about it. Hope to have some more images to show in the near future.
Okay, thank you, Oscar. And we're going to turn it over to Rob Dick. Just a second here. There we go.
Thank you. And I can't really compete against a lot of the people that take pictures and show them on in this part of the meeting. I try to dwell on serendipity, and also with the help of my son, who was up at 4 a.m., he pulled me out of bed to come up and take a look at the moon. And because of all the forest fires, there's a lot of particulate matter that filters out the red light. I'm sorry, the blue light. So here we had what looked like a very bright eclipse moon hanging up in the sky. And so got some pictures of that. This is actually concocted. The images of the house wall on the left and the tree on the right, they were taken with a 55 millimeter lens, and then we used a 400 millimeter telephoto lens to take picture of the moon, and then I reduced that down so it didn't look too godly awful, to show roughly what it looked like visually in the sky. I think it's kind of nice to show pictures that really reflect what it looks like to your eye. And yes, that usually means you have to corrupt it a little bit or change it to suit that. Cameras are so much better than your eye, and in some respects your eye is so much better than the camera, so it's rather difficult to make the scene look like what it appeared to be. So even though it wasn't an eclipse, it certainly looked like an eclipse, and hope to do more of these in the future.
Okay, thank you very much, Rob. We're going to turn over to Jim Sophia.
Okay, thank you. So these are two images of NGC 7662, the Blue Snowball Nebula, a planetary in the constellation Andromeda. These are large crop images of the snowball, whose apparent size is only 32 by 28 arcseconds, a small blue image, a bit smaller than Jupiter in the eyepiece. I used the Malincam Skyraider DS10C Tech and my 8-inch scope with a pollution filter, a light pollution filter for each image. And just to reiterate, the Malincam can take movies or videos, but also snapshots, and that's what you're seeing. The image on the left appears somewhat overexposed, with the central regions blown out, showing some gross detail. This is a combined stack of 4 15-second exposures, totaling a minute of exposure time. On the other hand, the image on the right was taken using a sequence of gradual exposure times. This is a live stack beginning with stacking 10 1-second exposures, then stopping the loop and increasing the exposure time to 2 seconds, then starting the loop again, stacking another 10 over that. I repeated this process up to 5 seconds with a final integrated stack of 50 frames altogether, totaling 2.5 minutes of exposure time, which is what we see now. With this approach, I see more visible detail in the core area, and we can also see the semi-transparent shell surrounding the nebula pretty well. No central star, though. I didn't want to blow out the central region, but perhaps more exposure time would have done the trick. Although I believe I see it lurking in the background. So in conclusion, varying the exposure time while live stacking is one way of preserving the dynamic range of luminosity that you can capture in certain images that have high dynamic range, like the blue snowball. Another example is M42, the Orion Nebula, where an overexposed bright core can obstruct our view of the interior. Thank you.
Okay, thank you very much. Andrea, who appears to be on the move here. Let me just replace the spotlight. There we go.
I'm in cottage country, so I'm trying to find a spot. This image here is the Iris Nebula that I shot through the Hyperstar system that I have, which is a Celestron C11 telescope. And I use just an IR UV cut filter. Next image, please. This is the Veil Nebula, and this was my first attempt to use a monochromatic camera. So I shot this image through a hydrogen filter and an oxygen filter, and then I assigned oxygen to blue and to green and hydrogen to red. So it's an HOO color palette. Next image, please. This is the Dumbbell Nebula. It's M27. And this was actually a really challenging object. I shot it again through the Hyperstar, which is about 540 millimeters focal length. And it had a really high dynamic range. So it was really, really bright. I was quite surprised. So I had a lot of fun trying to process this image to show the inner core, but I definitely saw an apple core with red and green. Next image, please. This was my first attempt at Milky Way photography. I went to the beach and I took several images and I stacked them to try to expose the core of the Milky Way. And this was shot from the cottage where my parents have a cottage. And next image. And this was, when I went to visit my parents, I had one clear night out of the 7 nights, and this was a close-up of the Rho Ophiuchi region. I shot this one with my dedicated astronomical camera, the ASI 2600 MC, and I used my Red Cat telescope for about 250 millimeter focal length. And this is basically my favorite image of last month, and I think it turned out pretty nice. And you can see the globular cluster M4, as well as all the nebulosity. That's it. Thank you.
Okay, thank you very much, Andrea. And now we're going to turn it over to Paul Clenninger. His video is off, so I'm going to show you a picture of him. There we go. And you're ready to go.
Great, thank you. We've still got Andrea's shot up.
She should, oh, sorry.
There we go.
Yep.
Thanks, Dave. Well, good evening, everyone. I hope your time under the stars lately hasn't been too badly affected by the smoke drifting through our region from the forest fires out west. As you've already seen here, it's certainly been noticeable photographically on some of our supposedly clear nights. My images tonight are from the cooler, clearer nights of winter and center on the constellation Auriga, the charioteer. Even though we tend to think of the summer Milky Way as prime nebula hunting territory, in winter it runs directly through this region of the sky, and as a result, there's a wealth of interesting nebulae and open star clusters to explore. Auriga is especially populated by some intriguing objects. Next one, please, Chris. So I captured this view with a 200 millimeter lens and Canon 60DA on a Star Adventurer mount. You can see that these objects are fairly large, with the moon inserted for just a comparison of size. Though the emission nebulas are fairly faint, the brighter portions can be observed visually with a telescope, especially the embedded star clusters powering the emitted nebular light. The open star cluster M38 is an easy and pretty visual target. IC 417 is part of the formation popularly known as the spider and the fly, though in my view, the fly seems to have managed to escape off the top of the frame. IC 405, the large nebula at the bottom, contains the variable star AE Aurigae and energizes and illuminates the surrounding hydrogen gas, giving the object the popular moniker of the Flaming Star Nebula. The star itself has an apparent magnitude of +6, making it just visible to the naked eye, if you know exactly where to look. Since this region is in the Milky Way, the whole area is awash with stars. That can make things tricky when it comes to imaging objects here, since the stars are pretty easily captured, but the much fainter nebulae require longer exposures. My target of particular interest tonight is IC 410, so I wanted a closer look at this one. Next one, please, Chris. So I captured this view with a 420 millimeter lens and Canon 60DA on an auto-guided star adventurer mount. So IC410 is a dusty emission nebula, approximately 12,000 light years from Earth, and is about 100 light years in diameter. The intricate gaseous structures within the nebula are lit by the intense radiation from the open star cluster NGC 1893 that lies near its center. This cluster of young, massive hot stars is only about 4 million years old, and images taken by the Chandra X-ray Observatory suggest that it contains approximately 4,600 young stellar objects. Next one, please. There we go. So to the upper right of the star cluster are two fascinating structures that fire the imagination and called for a closer look. These are the tadpoles. They're not too easy to make out at this scale, and they're also surrounded by the light of the surrounding emission nebula. But they're denser than that surrounding material, and that itself lends to a different type of imaging. Next one, please. So this view was captured with the higher resolution of my 11-inch Edge HD telescope and a QHY9M CCD astronomical camera using narrowband filters. This type of imaging is a bit challenging since the scope at f10 and a focal length of 2,800 millimeters isn't particularly fast, and the filters only allow very thin slivers of visible light to reach the camera. As a result, this image required a combined effort of over 10 hours of exposure. The filters themselves transmit light emitted at specific wavelengths by hydrogen, sulfur, and oxygen gases. The sulfur emissions are then mapped to the red component of this RGB image, and likewise, the hydrogen alpha emissions are mapped to the green and oxygen to the blue. This palette of colors is known as the Hubble Palette and is used in the Hubble Space Telescope narrowband views, as well as by most observers doing narrowband imaging. So the tadpoles are composed of gas and dust left over from the formation of the NGC 1893 star cluster at the center of IC410, and are themselves likely to form more stars in the future. These are really enormous structures, some 10 light years in length, over twice the distance between Earth and Alpha Centauri. Interestingly, they point away from the center of the nebula due to the stellar winds and radiation pressure from the hot stars in the NGC 1893 cluster. Their heads are scorched by those intense stars, and that forms the bright shock front of ionized gas outlining their forms. In time, the material forming the tadpoles will either be used in the creation of new stars within them, or will be boiled away into the surrounding space. A couple of fascinating objects indeed, swimming in the ocean of deep space. That's it for me this month. Thanks, everyone. Have a clear sky. Bye.
Thank you very much, Paul. And that's great. And let's move on to last month's observing challenges. We had Messier 15, IC 5146, Pease 1, and Crater Goldschmidt. What are our challenges for this month? Well, our beginner challenge is Messier 75 is a globular cluster in Sagittarius, about 68 to 1,000 light years away. And so that's our beginner challenge. Intermediate challenge is Barnard 93, a dark nebula in Sagittarius. And our advanced challenge is IC 4616, a spiral nebula in Hercules. All of these challenges will be in our Amazing Astronauts articles coming out soon. And our lunar challenge is Dorsum Zirkel. It's a wrinkle ridge in a Mare Imbrium and 193 kilometers long. So there's a summary of our observing challenges, and thank you to Oscar for continuing to pull these together for us. RASC calendars are now ready to order. You can order them on our website. There's a form that you fill in, and there's different local pickup points within Ottawa for the calendars. Deadline is October the 15th. Once we have all our orders in, we'll place them. And there's 4 locations in the Ottawa area where you can pick them up, one of them being my place. Cost is $16 per calendar for members and $15 each for 2 or more. Non-members, it's $20 per calendar. There's no quantity discounts for non-members. We are going to get Chris to speak to this here. Just a second. Let me just highlight you. There we go.
Thanks, Dave. This is just a reminder from a slide of a previous month. The RASC Ottawa Centre is lending astronomy support to a music performance that will take place next weekend in the Pontiac. There'll be a particular interest performance of the planets, and Jim Thompson will be giving live streaming images from his telescope there, as well as Stefan Papa of the Astro Pontiac will be giving a talk on astronomy in general and the Perseid meteor shower, which should be peaking right at that time. So tickets are available online if you want to combine astronomy and music in a beautiful setting in the Pontiac.
Okay, thank you, Chris. Fred Lawson Observatory. It is open, limit of 100 people on the site, outdoors, 5 people with masks in the observatory itself. And yeah, it's excited that we're quite excited this stays open. Let's just hope our COVID numbers continue to stay down. Here are the folks that help keep the club running. The Stanmont Book Library is currently closed. It's located within the Aviation and Space Museum. And once we get back in there, you'll have access to those. We have...
I've seen a maximum of 57 people at any one time.
57.
So we've probably had 60 to 65 total, a low number, but typical of the middle of the summer months.
Yeah, midsummer. Yeah, so that's fine. Thank you for everybody who participated here this evening. And a special thanks to Bob Olson for his amazing presentation. So if you would like to join the RASC, we have regular memberships at $88, family memberships $82.50 plus $15 per adult, $8.10 per youth. And we also have youth memberships, which are $53 for those under 21 or under 25 if they're still a student. What do you get with that membership? Well, locally, you get access to the Fred Lawson Observatory out near Almont. We have a telescope loan library. Once the museum reopens, we'll have access to the book library as well. In addition, you'll get the local Astronauts. It's an electronic publication sent out monthly. The editor is Gordon Webster. Every 2 months, you get Sky News. Every 2 months, you'll get the Journal. And once a year, you'll get the Observer's Handbook. Some of the benefits of being a member of the RASC. So our next meeting is September the 10th. We always have to skip the long weekends. So it's one Friday. It's the second Friday of September. And we have a guest speaker who's going to be talking to us about the southern skies, the skies in the southern hemisphere. Should be quite fascinating, a fellow from Toronto. And I may have one other person as well. But right now, that's what the plans are for the September 10th meeting. So thank you, folks, for coming out tonight. And we look forward to seeing you after Labor Day.